Here we go. Okie doke. So this is kind of where we left off last class, as we were talking about Syndihydroxylation. And really, all you need to know about Syndihydroxylation are the reagents that can affect a Syndihydroxylation, which are summarized on a slide after this. But you need to know that Syndihydroxylation results on the addition of the two hydroxyls on the same face of the molecule. I'm not going to ask you about a cyclic osmate ester or this mechanism that is shown here. But as long as you know and understand that this mechanism is a concerted process, right? It all happens at the same time, then you would know that the cyclic osmate ester is going to end up with both of the bonds to oxygen being on the same side of the molecule. And therefore, when we do the workup or the second part of the reaction with sodium sulfite or sodium bisulfite, that we end up with a cis diol, right? We end up with both of those hydroxyls on the same face of the molecule. Now, I told you that the problem with this reaction is that it's osmium tetroxide is really toxic. In fact, I even worked with somebody who refused to work with osmium tetroxide. She said it's too dangerous. And so you might be wondering, is there a workaround? And yes, there is. And we talked about this last class too. The two workarounds would be these two possibilities here. You can either use a catalytic amount of osmium tetroxide in this interesting molecule here, which is called NMO, which stands for N-methylmorpholine N-oxide. So an N-oxide is a new functional group. It's not really covered a lot in our textbook, but this is called an N-oxide here. Anyhow, I'm not going to ask you about that. All you have to know is that the NMO acts as a co-oxidant. What it really does is it just recycles the osmium tetroxide over and over. And the mechanism for that is not covered in our textbook in any way, shape, or form. Instead of using NMO, you can also use tert-butyl hydroperoxide, which we can abbreviate like this. So this molecule, you can just abbreviate it like this. It's a little bit faster. And of course, again, the amount of osmium tetroxide that's required is a catalytic amount because that tert-butyl hydroperoxide just serves to recycle the osmium tetroxide over and over and over. So really, you've got 4 or 5 different ways that we've learned. The ones that were on the last slide, these two, which use a catalytic amount of osmium tetroxide. And then I told you at the very end of our last lecture that you can also use potassium permanganate and sodium hydroxide in keeping the reaction mixture cold. And I said the only caveat to that is that if you have any other groups in the molecule that can be oxidized, oftentimes potassium permanganate can really just oxidize even things that you don't want to oxidize, right? That's why they call it research. You know, if you're wondering why, Mr. Dion, would I need so many ways of doing the same darn thing? Because if you're working in novel research, something that's never been done before, you say, okay, well, I want to make a cis diol, so I'm going to do a syn addition. And let's say you start by trying osmium tetroxide and NMO, and it doesn't work, or it gives you a poor yield. What do? You move on to something else. You say, well, I'll try this. You know, that doesn't work. Well, I'll try. You know, you have to kind of have a sort of a good background of all kinds of different reactions that can be attempted. Okay, so a good organic chemist, she or he will always have more than one way of doing every kind of transformation. And that's a theme that comes up over and over in our textbook. We learn more than one way to do several reactions throughout the textbook. All right, well, let's move on from there. And let's try some questions. This is question 8.24. It says, predict the products that are expected when each of the following alkenes is treated with a peroxy acid like MCPBA. Remember last class, I told you that MCPBA was this. It's metachloroperbenzoic acid, and it's nothing more than a peroxy acid, okay? And the peroxy acid, when we take it, or we take our alkene and we treat it with the peroxy acid, so this is MCPBA, so we'll put MCPBA. And then in the second step, we treat it with aqueous acid, which is just hydronium like this. Can anybody tell me what the result of this would be? Can anybody describe it? Would this be a syn-dihydroxylation or an anti-dihydroxylation? Maybe I should have titled this slide syn and anti-dihydroxylation. Could anybody tell me? Has anybody been studying or remember what we covered last class? Yeah, it's going to be an anti-dihydroxylation, isn't it? Right, because after the first step, right, after you treat this molecule with MCPBA, you make an epoxide or an oxirane. So you make an epoxide. So let's say you have the epoxide that looks like this, right? That's pointing down like this. Well, in the second step, when you treat that with, so this is after step 1, after step 2, you pop that open and you end up with a trans diol. So one hydroxyl is going to be pointing down and the other one is going to be pointing up like this. So you end up with a molecule that looks like this. So you would end up with this molecule plus its enantiomer. So this is a anti-dihydroxylation, right? And we end up with a trans diol like that. Okay. The next one is maybe more in the vein of the actual title of the slide. Okay, it says predict the products for each of the following reactions. Make sure to consider any chirality center. So if I take this molecule, which is trans, this is trans 2-butene. I would love to practice my nomenclature along the way. I take trans 2-butene. I treat it with a catalytic amount of osmium tetroxide and NMO, N-methylmorpholine N-oxide, which is my co-oxidant, which basically just recycles that osmium over and over. Well, I get Syndihydroxylation or trans dihydroxylation. Who could tell me? Sin or anti is what I meant. Yeah, sorry, I'm mixing up my words here. Yeah, so Josh says it's going to be syn, right? They're both going to be added to the same face of the molecule, right? These conditions result in syn dihydroxylation. Okay, so both of those hydroxyls are going to end up on the same face of the molecule. So we'll draw the skeleton like this. We'll put one of them being up like this and the other one being down like this. This is not a meso compound. Okay, this is not a meso compound. I'll prove it to you because if you rotate this bond, you end up with this molecule where you have this one up like this and this one down like this. So not only do you get that molecule, but you also get its enantiomer. All right, next conditions are potassium permanganate and sodium hydroxide. Cold temperature, go back here. I told you that when you do that, you get syn dihydroxylation. So that means we're going to get the syn product. And if we draw that out, it's going to look something like this, where we have our cyclohexane intact, like this. We'll put one of the hydroxyls pointing up and the other one pointing up. Son of a gun. Why, Lord? Why? There we go. We'll draw the other one pointing up like this. Will I get an enantiomer for this compound? Yes or no? No, there's not going to be. Why would I not get an enantiomer for this compound? There's 2 chiral centers. Yeah, you're all right. It's because it's meso. So this is a meso compound. So that's the only product you'll get. All right, that brings us to the very last new reaction that you'll learn in this chapter. You do not have to know the mechanism. The mechanism is really only covered briefly in our book, but I'll have to admit, and I told you this earlier, that this section, 8.12, has the best skill builder in the entire textbook in it. And I'm going to show you how that skill builder works. So this reaction is called oxidative cleavage. If you take an alkene, carbon-carbon double bond, and you treat it first with O3, who could tell me what O3 is? Could anybody tell me what O3 is? Well, the name is on the slide, right? This is ozone. And you're like, the same ozone that's in the ozone layer? Yes, the same ozone. Fortunately, we don't have to go up to the ozone layer to grab some ozone. You can actually make ozone in the lab very easily with an instrument called an ozonizer. I'm not going to go into that right now. So ozone in the first step, and in the second step, you treat it with DMS. DMS stands for dimethyl sulfide. Okay, and dimethyl sulfide is this, 2 methyl groups, and it's a sulfide, right? A sulfide is a sulfur analog of an ether. So dimethyl sulfide, like that. Dimethyl sulfide is one of the stinkiest compounds you'll ever work with, okay? Smells horrible. In fact, and I could be wrong, but I think that sometimes dimethyl sulfide is actually used in refineries where they have, so many pipes where they do, petroleum refining. And I think that they dope or put, small amounts of dimethyl sulfide in the process, so that if there's a leak in a pipe, the people who work there would actually detect it with their nose. So it's so stinky in such small amounts. And if you look at our textbook, there's an option besides using dimethyl sulfide. In some, I wouldn't want to use it if I don't have to, because it smells so bad. So instead of dimethyl sulfide, you can use zinc. Okay, zinc and water. So this is another possibility. I don't think it ever comes up in the solutions manual. My students have told me that, it doesn't come up in the solutions manual, but it is mentioned in the textbook. Okay, so to go from the alkene to these two aldehydes here, what do? Let me show you. This is the skill builder. I've redrawn this molecule in the top left here. You literally take an eraser, okay, and you erase the bond in the middle, okay, like that. Then you put in some what happened there? Okay, you do that. Then you add in some oxygens like that at the ends where you erased it, and those are the two new molecules, okay? You end up with this ketone and this aldehyde, and that's it. That's how you decide, or that's how you determine what the products are going to be. Again, the textbook goes into a little bit of detail about the mechanism. So you form what's called a molozonide, then it rearranges to a ozonide, and then the reducing agent, which is either sorry, this is the second step. So it's either DMS or it can be zinc and water. Either one works. You don't need to know this mechanism. Look, it's very rare for me to write something like that in red. This would be, I'd consider this a higher level mechanism, kind of beyond the scope of our course. But you know what? It's always interesting to take a look at these kinds of mechanisms. So again, just remember that the reducing agent, that's the second step, can be either dimethyl sulfide or zinc and water. And again, the skill builder shows you the really simple way of doing it. Let me demonstrate it one more time here for you. So 8.28 says just predict the products. If we treat the molecule with ozone first, O3, followed by DMS. So look, if I draw this molecule a lot bigger, okay, so this is kind of a ridiculous size, but whatever. Here we go. Let me draw this one here. What you would literally do is take your eraser and you erase the middle of that double bond and you erase the middle of this double bond, and then you put oxygens at the end. So you'd have an oxygen here, an oxygen here, an oxygen here, and an oxygen here. Those are the two products that you get. Now, if you drew them that way, I mean, technically it's correct, okay? It's kind of a goofy way of drawing them, but it is correct. I would try to draw it a little bit prettier. This one's pretty fast. This is a small molecule called acetaldehyde, which we'll look at more later on in the class. So you get this molecule, plus you have how many carbons in this chain? You can count it up. You got 1, 2, 3, 4, 5, 6, 7, 8. So you can go like this. Just do 1, 2, 3, 4, 5, 6, 7, 8. And on carbons 2 and 7, you have a carbonyl. And then on carbon 1, 2, 3, 4, you have another carbonyl. And so those are the two products. Give me a thumbs up if you're like, I think I can do this. I like this. Just give me an eraser and I can figure it out. Anybody with me on this one? Yeah, cool. It's a really simple skill builder. It's a very simple way of looking at it, but it definitely works. It's going to work 100% of the time. Okay, so let's take a look at the next one quickly. Oops, I don't know why it does that sometimes. So I'm just going to erase that because it's covered in the skill builder. The next one, might be a little trickier, but if we take that molecule and in the first step we treat it with ozone, and the second step we treat it with dimethyl sulfide, right, what are we going to do? I'm not going to use the eraser trick this time. I'm just going to say we're going to break that bond here. So now instead of having a bicyclic structure, we're only going to have one ring left, right? The only ring left is going to be this part here. Now, it might be a knee-jerk reaction to say, okay, well, I'll draw it, like this. So I'll have this part, then I have a carbon, then I have another carbon here, and both of these are going to have, double bonds to oxygen like this on them, okay? There's nothing wrong with that, technically. I'd say there's nothing wrong with that. But I think a better way to draw it, since there's only one ring in the molecule, would be to draw it like this, where it's a 5-membered ring, and we have these two hydrogens here, right? There's a hydrogen here and hydrogen here, so you can see that the hydrogens are going to be pointing the same way, right? And the two aldehyde groups are going to be pointing the same way, so you could just draw it like this. Just say, okay, well, I've got, oops, where's my red pen? There we go. So you could say, okay, well, I'm going to have, this guy pointing down, this guy pointing down like this, and this is a meso compound, right? Like that. Again, if you drew it like that, technically it's correct. But if you look at the textbook, I'm pretty sure he doesn't draw it like that, right? If you don't draw monocyclic structures like this, okay? And there's only one ring in the molecule, right? There's only this ring, which is a 5-membered ring. All right, there we go. So with that in mind, the last 2 sections of the textbook just deal with strategies and some practice. So I'm going to go over these or section 8.13 and 8.13 a little bit quick so that we can really get into 8.14, which is going to be the focus of the rest of the class, which is going to be just some practice. So, if you're overwhelmed when you're studying, you're just like, oh, there's so many reactions. Well, first of all, go back to what I told you on the first day of class, which is, why is organic chemistry such a good litmus test or such a good predictor of success in professional schools like a medical school? Well, there's 3 reasons. Okay. Number 1, it's the sheer volume of content. We cover a lot of content. Number 2, we cover it quickly. And number 3, you have to be able to remember it, right? In order to be an MD and to get through medical school, you have to be able to cover a lot of content quickly, and you've got to be able to remember that. So, anyhow, 8.13, and I realize that not everybody in the class wants to be an MD. I totally get that. But the skills are still the same. Anyhow, so first step, you're going to look at the reagents, right? So you're going to want to know what all of the reagents that we've looked at in this chapter, what they do. BH3 THF followed by hydrogen peroxide, sodium hydroxide, anti-Markovnikov addition of water, right? You want to know every single reagent or set of reagents that we've looked at. Then you want to know about regioselectivity. Is it Markovnikov or anti-Markovnikov? Stereospecificity. Are we dealing with syn or anti-addition? Now it says here, and this is kind of what I've been getting at, or what I've mentioned several times in this chapter, is that only a little bit of reagent memorization, but a firm grasp of the mechanisms can really help you out with this chapter and the chapters that follow it. The more familiar you are with mechanisms, the greater comprehension you have of mechanisms, the easier predicting products will be. And this is how organic chemists that develop new reactions, this is how they discover new reactions, is that they do have a good understanding of how atoms and molecules are going to react, and they can make predictions, and then they base their research off of that. So in section 8.14, and this is kind of where we're going to end, we're going to spend the rest of the time talking about synthesis for the next 3.5 hours. So in chapter 8, we spent a lot of time looking at addition reactions, but substitution and elimination, these were covered in chapter 7, and we're going to use these reactions, the chapter 7 reactions, a lot in the remainder of this lecture. What if you just have a simple one-step synthesis, right? If you take this exocyclic alkene, so this alkene shown right here, and you want to make this tertiary alcohol, well, it's a Markovnikov addition of water across a double bond. There's no carbocation rearrangements to consider here, so all I would say is just treat it with aqueous acid, right? And we do a Markovnikov addition. You should be able to draw the mechanism of that, right? You should be able to draw the mechanism pretty quickly, that you get the proton transfer. In the first step, you make the tertiary carbocation, then water comes in as a nucleophile, and I'm not going to draw the entire mechanism right now. You make an oxonium, and then it gets deprotonated, so you should be able to draw that mechanism of that Markovnikov addition of water across a double bond. What if you want to change the position of a leaving group, like a bromide? How would we do that? I want to just make this bromide or bromine dance from this carbon over to this carbon. How do you do that? How do you move it around? Well, we know a way to do that, right? What if you could eliminate that bromine in the first molecule? What if you could do an elimination to make the Zaitsev product? Right? How would you do that? You'd simply treat it with a non-hindered strong base like sodium methoxide, right? And you make the Zaitsev product. And then if you want to put the bromine on the other carbon, it's just going to be a Markovnikov addition, right? You're just going to use HBr, and that's because this is a Markovnikov addition, right? So you see how you can put chapter 7 material together with chapter 8 material. So you're going to have to be kind of Johnny on the spot with all those reactions. Again, what if you wanted to put the double bond, over here? Well, in that case, you'd want to make the Hoffman alkene, so you'd use a hindered base. You could take that Hoffman alkene and you could treat that with HBr, and it's not on here, but you could treat that with HBr and peroxides, and then you'd move the bromine over onto this carbon. So you can see how you can move that bromine around the molecule using the reagents that we've learned in the past 2 chapters. So it shows you here some different strategies. I'm just going to move on from there. Here's another good example. What if you wanted to take a hydroxyl, which is not a good leaving group, and you wanted to move it from this carbon onto this carbon, right? How do you do that? How do you move it from the yellow carbon onto the green carbon? Well, this is, an example of where we can use what's called retrosynthesis, which is kind of thinking backwards. So if you look at this and you say, I have no idea how to do this. Well, what I would think is this. A good strategy might be if I went backwards, and that's what this arrow means. This is called a retrosynthesis arrow. It means you're going backwards, backward synthesis, okay, which is not a thing, but it's just a tool for us to think backwards. If I had this alkene, right, if I had that alkene, all I would have to do is an anti-Markovnikov addition of water, right, using borane and THF followed by hydrogen peroxide and sodium hydroxide, right, anti-Markovnikov addition of water. So then the question becomes, if I had this alkene, I'd be home free, right? I'd know how to make this guy. Is there a way I can make that alkene from that alcohol? Well, sure there is. Sure there is, right? If I was to convert that alcohol into a good leaving group using toluene sulfonyl chloride, or TSCl, and pyridine, right, then I'd convert this to the tosylate, okay? And then I could do an elimination to make the Hoffman alkene. So I would use a bulky base like potassium T-butoxide that would give me that alkene. And then in the next step, I would treat it with borane and THF in the first step, and hydrogen peroxide and sodium hydroxide in the next step, right? That's the kind of strategy that we want to take to solve these kind of problems, and the solution is shown down here. I just wrote the solution on the previous slide. So there you go. You have a synthesis. How many steps is it overall? You got step 1, step 2, and then you get steps 3 and 4. Now you might think that's a lot of steps, but later on in this class, we're going to look at syntheses that have, up to 8, 9, 10 steps sometimes. Not all the time, but once in a while we'll look at syntheses that are pretty long. All right. And if you're wondering, what's the longest synthesis that's been developed? Well, after you get to a certain number of steps, the yields get really low, the overall yields. But I don't know, there's been, natural product syntheses that have over 30 steps. So something to think about. We obviously don't look at anything like that in this class. What about moving the position of a pi bond, right? Pi bonds, we learned in this chapter, are great tools for adding elements to or molecules to. If we wanted to take this tri-substituted alkene and convert it into this mono-substituted alkene, what would we do? Well, we could just do a anti-Markovnikov addition of HBr across the double bond, right? We would use HBr and a peroxide, and then we would do an elimination with a bulky base, T-butyl or potassium T-butoxide, like that. Okay, so just another strategy there. So these are all the reactions that we've looked at in this chapter. I think it's better if we look at them on this slide here. So you need to be familiar with every single reaction that's on here. Now, I told you that I'd tell you exactly which mechanisms you need to know. So let me go over that. And I'm going to put a star by the ones that you need to know the mechanisms. So mechanisms to know. So we'll put the red star of solar federation by that, okay? So you need to know hydrohalogenation. You don't have to know number 2, which is anti-Markovnikov addition of HBr, because I told you that's a radical mechanism. That's going to be covered in chapter 10 mechanism. So I'll just delete that because I don't want anybody to think I don't need to know that until I do chapter 10. The next one, which is a Markovnikov addition of water. Hell yeah, you get to know that mechanism. Oxymercuration, demercuration. This one here, you do not have to be able to draw that. However, we did go over it to some extent, and it helped us understand why we get Markovnikov addition with no carbocation rearrangements. Same thing with hydroboration oxidation. I'm not going to ask you to draw that mechanism. However, we did go over it in class. The first step, mostly. The second step is covered in the textbook, but the first step is the one that helps us understand the regioselectivity and the stereoselectivity of the reaction. I'm going to put a star by this one. I'm probably not going to ask you to draw the surface of a metal, and show hydrogen sticking off of it. But you know what? We spent enough time talking about it that I think it's important that you understand that mechanism so that you understand the syn addition of hydrogen when we do a hydrogenation reaction. Hell yeah, you got to know the mechanism for halogenation with bromine or chlorine, right? Remember that proceeds through a bromonium ion. For the same reason, you need to know the mechanism of hydrohalogenation. It's the same as this mechanism, except instead of bromide being the nucleophile, water is the nucleophile. I wish I could put a star by this one because I would like you to know that one, but it's we kind of made an agreement, me and the other instructors in organic chemistry here at UCCS, that we're not going to ask that one. I think it's a really cool one, so let me put that in a yellow. If you want to, I'll say optional. You don't have to know it. You don't have to know the mechanism of potassium permanganate, Syndihydroxylation, any of the Syndihydroxylation mechanisms. So none of those have to be known. So there you go. But those are all of the reactions that we covered in this class. Now, how do you memorize these reactions? Well, that depends on the student. Everybody is different, but you've got to find a way to remember things, right? Part of the, probably one of the biggest things I learned in university was how to study, and how to enhance my learning capabilities, because I'm sure that if I was to go around and ask most of you, did you find high school easy or difficult? I would wager that the vast majority of you would say, I found high school, not that challenging. And so, university is something else. It's a higher level, especially when you get into a class like this. So let me give you some ideas. Personally, I think there's something to be said for writing things down. The more that you write these reactions down, just the better the more they become ingrained in your memory. And there's some kinesthetic learning properties that I'm not an expert on that, but there's definitely some learning properties in writing things down. Let me tell you another interesting story about a student that I had not that long ago. I think I had this person as a student a year ago or a year and a half ago. We came back after the summer, and this person started Organic Chemistry 2 with me in August. And, since you are taking Organic Chemistry off sequence, if you take Organic Chemistry 2 it's starting in August, you kind of have the summer off where you might not think about organic chemistry. But we came back, and I started asking them about reactions they had learned in Organic Chemistry 1 that most people hadn't thought about since May. And this one gal in my class, she knew every stinking reaction. She knew them better than when the class ended. And I said, I can tell you her name. I said, Madison, how did you do it? How do you know all these reactions? Like, you're even better than you were when we stopped, And she said, well, I worked in a grocery store. And she said, how when you work in a grocery store, you wear like a smock or whatever. And anyhow, maybe some of you have worked in a grocery store before, but she said that she made a big key ring, and she had every single reaction we learned on 3x5 cards on that ring. And she said, whenever I had a second, I would take that thing out of my pocket and I would look at it. She said, after the first month, I knew the reactions frontwards and backwards. So, it's repetition, right? And, why is somebody who's been studying organic chemistry a long time, why do they know so many reactions? They've seen them over and over and over, So that's just a strategy that you can use, okay? Anyhow, and of course, you can talk to your classmates and maybe they have ideas, or maybe there's ideas on YouTube. There's probably people that make songs up about this kind of stuff, so you turn it into an earworm. Anyhow, who's ready to do some practice? This is where the rubber meets the road, my friends. Now we're really going to get into it. Okay, just me. Okay, I thought maybe somebody would be super pumped to learn those. Any questions about that? All those reactions that we've looked at this chapter before we start really getting into some practice? If not, okay, let's get cracking McCracken. Okay, 8.31. I'll call this A. I'll call this B, and I guess I'll call that C. Could anybody tell me what's happening in the first reaction? And you can give me a shorthand answer, or you can unmute your mic. What's happening in the first reaction? BH3THF followed by hydrogen peroxide and sodium hydroxide. What's going to happen in this reaction? Could anybody tell me? Is anybody there? Is it frozen? No. Yeah, you're in the right vein. Okay. So boron and THF followed by hydrogen peroxide and sodium hydroxide. Could anybody tell me what the result of this is going to be? We spoke about this is hydroboration oxidation. Okay, that's the name of the reaction. Yeah. But what does it do? What are we doing in a hydroboration oxidation? What's the result going to be? How would you describe it? What molecule are we adding across the double bond? Even if you could just answer that. What molecule is being added, right? We're talking about addition reactions in chapter 8. That's the title of the chapter, addition reactions of alkenes. So we're adding some molecule across the double bond. What's the name of that molecule? I'll give you a clue. You're made out of this molecule, mostly. Exactly. It's just an anti-Markovnikov addition of water, right? And Chris is saying it also occurs by a syn stereoselectivity. Right now, in this case, we don't have to worry about the syn addition so much because you don't end up with any chiral centers. But you're right, Chris. Absolutely. So this is going to be an anti-Markovnikov addition of H2O, right? Markovnikov is the rich get richer. And so the rich one is this one here. So instead of that one taking the hydrogen, it's going to take the hydroxyl. And I'm going to end up with this primary alcohol. So anti-Markovnikov addition of water. What molecule am I adding across the next? What small molecule is being added to this alkene in B? Could anybody tell me what molecule is being added in B? Right? It's a hydrogenation reaction, right? Which occurs via a syn addition. So this is syn addition of hydrogen. So we'll start by drawing our alkene, or our skeleton, I should say. I'm just going to draw the parts of the molecule that are going to be unaffected. I'm going to draw both of the hydrogens pointing up like this. If I have one pointing up and this one pointing up like this, that means that this methyl group is going to be pointing down like this. Now, this is not a stereo center, but if that helps you, it's totally fine. I'm going to delete it. Okay, I'm going to delete it like that because it's not a stereo center. And so we're going to end up with this molecule, plus we're going to end up with the enantiomer of that molecule. If you're like, what do you mean by the enantiomer, Mr. Dion? All I mean is that you can get syn addition from both faces of the molecule. So if I copy this and put it over here, okay, I'm going to end up with this molecule, and I'm also going to end up with this molecule where the methyl group is pointing up like this. I'm going to leave the hydrogen out this time. Okay, in fact, if you look at the solutions manual, I'm sure that he leaves all the hydrogens out and just draws, the two methyl groups as being up and down, right? And the relationship between these two compounds is that they are enantiomers of one another. The next one, remember that this is a peroxy acid. So this is a peroxy carboxylic acid. So peroxy acid in the first step. And in the second step, I treat it with hydronium. Could anybody tell me what's happening in this, or what's going to happen in this reaction? Would this be a Syndihydroxylation or an anti-dihydroxylation? So I'm taking a peroxy acid and then I treat it with water. It's an anti-dihydroxylation, right? Anyhow, this is one of those ones that I said I wish that we had to know the mechanism, but you don't. So what are we going to end up with? Well, I'll draw the skeleton like this, and I'm just going to draw one of the hydroxyls pointing up like this, and I'll draw the other one pointing down like that, and then I'll draw this methyl group like this. You're going to end up with this compound, plus you'll end up with the enantiomer of that compound. All right, there we go. So we've already got some practice. Let's keep going. It says predict the products of the following reactions. I'm going to go a little bit faster here. The first one, we're taking this alkene and we're treating it with osmium tetroxide and then sodium bisulfite in water. So that's going to give us a Syndihydroxylation. So Syndihydroxylation, like that. So let's start out by drawing the skeleton. And by skeleton, I kind of mean the part that's not affected. Okay, so now on my double bond, I'm going to have one hydroxyl pointing up, and I'll have the other hydroxyl pointing up, which would mean that this methyl group is going to be pointing down. So I'll end up with this molecule plus its non-superimposable mirror image, which is its enantiomer. Okay, who could tell me what's going to happen, or just describe what's going to happen in the next reaction? I'm taking this alkene and I'm just going to treat it with aqueous acid. Right, so you take that alkene, you treat it with dilute HCl or something. What do you think is going to happen there? Or could anybody describe it? And if you have to unmute your mic, go for it. This is the land of the free. Did anybody tell me what's happening here? Tell me what molecule I'm going to add across the double bond with hydronium. Thanks, Chris. It's just a Markovnikov addition of water. Will there be a carbocation rearrangement? No. And if you're unsure about that, you could just draw the intermediate, right? You could draw the intermediate carbocation. I'm not going to draw the mechanism right now. We've gone over this mechanism, but you would end up with the rich getting richer, right? So you'd end up with this tertiary carbocation here, which is not going to rearrange. And then after the nucleophilic attack and proton transfer, you would end up with a tertiary alcohol. So you end up with this tertiary alcohol, and it does have a chiral center. This is a chiral center right here. And so we'd end up with that molecule plus the other stereoisomer. It's enantiomer. Okay, next one is a Markovnikov addition of HBr across a double bond. This one, let's slow down maybe and draw the mechanism. Right? How do I know this is Markovnikov? Because there's no peroxides. So this is going to be a Markovnikov addition, right? The double bond is going to take that hydrogen to produce a carbocation. Let's draw the carbocation out. Okay, it's going to be this carbocation here. And so what's going to happen next is that the bromide is going to act as a nucleophile now. And it's going to attach itself here, and we end up with a chiral center, right? We end up with a chiral center in the molecule, and so we're going to end up with that tertiary alkyl bromide. Put my dimethyl group over here, okay, like that. So I'm going to end up with, oh, did I say there was going to be a chiral center? I don't know what I was smoking. There we go. So there's no chiral center in that molecule, my mistake. All right, so this is called hydrohalogenation, right? A hydrohalogenation mechanism. All right, here we go. So some more practice. Let's keep going. Let's keep going. Now we're going to solve it or look at these problems from a different point of view. Now we're going to have to choose the reagents. So we've been given the starting material and the product. Okay, so let's call this one A, we'll call this one B, and we'll call this one C. So what am I doing here? Who could tell me what's happening or what kind of reagents I would have to use to do this first transformation to go from this alkene to putting the hydroxyl on this carbon? The rich are not getting richer, are they? Right? This carbon is the one with the most hydrogens. That vinylic carbon has one hydrogen. There's no hydrogens on this vinylic carbon, and the hydrogen is not going here, rather a hydroxyl. So this is not a Markovnikov addition. Can anybody tell me what's, It's a hydration. Yes, we're adding water, but it's anti-Markovnikov hydration, right? So this is anti-Markovnikov addition of water, right? So what are the conditions for the anti-Markovnikov addition of water? In step 1, we need BH3 THF, or borane THF, and in the second step, we need hydrogen peroxide followed by sodium hydroxide. So that means not only do you have to be able to draw the products, but you've actually got to be able to come up with the reagents. Okay, what about B? Could anybody tell me what's happening in B or what the reagents would be? Anything to do with B? Is this a Markovnikov or an anti-Markovnikov addition in B? Would the addition in B be Markovnikov or anti? Yeah, it's anti-Markovnikov addition of HBr, right? How do you know that, Mr. Dion? Well, look, this vinylic carbon is richer in hydrogens, and there's still just those 2 hydrogens, right? That carbon took the bromine, whereas this carbon takes on a hydrogen. So this is an anti-Markovnikov addition of HBr, right? Anti-Markovnikov addition of HBr. So how do we do that? We use HBr and peroxides at the same time. All right, what about the next one? The next one, could anybody tell me what I would use or what's going on here? Any information would be appreciated. Yeah, Josh just says throw HBr at it, right? Because the next one is a Markovnikov addition of HBr. So all we need for that is just HBr, nothing else. There we go. So as the class progresses, you're going to see more and more questions like this, where you just have to come up with the reagents. So let's try some problems that are maybe a little more complex. We want to come up with some reagents for these. And so in order for me to have enough space to solve these, I'm actually going to move to a blank sheet here. So just give me a second. There we go. So this is 8.37. 8.37. We're going to start with A. So we'll start with this molecule, and we want to make this molecule. We have a methyl group and a chlorine here. Okay, there we go. Oops, that didn't work, did it? Just want to tidy that up. There we go. So what we're trying to do is we're trying to move the chlorine from that green carbon over to this yellow carbon here. Right? That's all we're trying to do. Now, if I was to treat, let's say, if I think backwards, if I had this alkene, if I had that alkene, all I would have to do is a Markovnikov addition of HCl to that alkene in order to make the product. So the question then becomes, how do I get from this alkyl halide to this alkene? Right, that's the question. If I was to treat this with a sterically hindered strong base like T-butyl potassium T-butoxide, I would end up with the Hoffman alkene. Right? I'd end up with the Hoffman alkene, which doesn't really help me a whole lot. That doesn't get me any closer to where I want to be. So could anybody tell me how to make this alkene in the yellow box? What reagent would I use to make that alkene? Yeah, I'd use an unhindered base, right? You want a strong base. Patty's saying sodium methoxide. You could use sodium ethoxide or sodium methoxide. Either one is going to work. I'll say sodium methoxide just because my student did. So sodium methoxide, which is written like that, that will give me the Zaitsev product, won't it? Right, this is an unhindered base. And so I end up with the Zaitsev product. Zaitsev product. And then all I have to do is a Markovnikov addition of HCl across the double bond. Right, so I'm just going to treat it with HCl, and this is a Markovnikov addition. Right, the rich are getting richer. This is the vinylic carbon that has the hydrogen, and that's the one that's taking the hydrogen from the HCl, right? It's taking this one. There we go. Give me a thumbs up if you're following me, because these are very important skills. You're probably realizing that they have to be practiced, and I understand that. I totally get that. Yeah, they have to be practiced, and it takes a lot of repetition in order to master these concepts, these reactions. Okay. Well, let's try another one. So let's try 8.37b. This is 8.37b. We're going to take this secondary alcohol. We're going to take that secondary alcohol and we're going to convert it to this primary alcohol. So we want to move it from the yellow carbon over to this green carbon. Now, I know this isn't easy over Microsoft Teams, but does anybody have an idea, any kind of strategy that we might take here? How would I get from the starting material to the product? Okay, well, if you're not sure what you should do, the first thing I notice is that a hydroxide or hydroxyl is not a good leaving group, right? It's not a very good leaving group. And what Patty is saying is, will a hindered base be used? And you're absolutely in the right vein, because if we think backwards, right? Remember this double line with an arrow pointing on it? That's called a retrosynthesis arrow. It's just thinking backwards. What if I had this alkene? Right? If I gave you that alkene and I said, I want everybody to take that alkene and make this alcohol, all that is an anti-Markovnikov addition of water across a double bond. So borane THF followed by hydrogen peroxide with sodium hydroxide, right? This is just step one is BH3, THF. The second step is hydrogen peroxide followed by sodium hydroxide, right? Everybody should be able to do that. And so the question then becomes, how do I get from here to here? And that's what you're saying, Patty, is you're going to have to use a hindered base to make that Hoffman alkene. Well, how do I convert that alcohol into a good leaving group? Remember that we went over how to do that, and you treat it with toluene sulfonyl chloride, TSCl, in pyridine, and then you make a tosylate. And a tosylate is a good leaving group, right? This is a poor leaving group. This is a good leaving group. Why? Because a good leaving group is the conjugate base of a strong acid. Toluene sulfonic acid is a strong acid. Water is not a strong acid. So now we've made a good leaving group. And if we take that compound with that good leaving group and we treat it with a hindered bulky base like potassium T-butoxide, it's going to remove one of these non-hindered protons as opposed to one of these more hindered protons, right? And if we draw the mechanism out just for fun, so this is the T-butoxide, what it's going to do, it's going to pluck this arrow here in an E2 mechanism to give us this terminal alkene. And when I say terminal, it just means it's at the end of a molecule like this. So that's our terminal alkene. It's not very pretty, but anyhow. And then for the last step, I take it and I treat it with borane and THF, followed by hydrogen peroxide and sodium hydroxide to affect the anti-Markovnikov addition of water. Well, with that in mind, let's take a look at another one. So let's try 8.37C. This is 8.37C. If we want to take a secondary alkyl bromide, like this one here, so here we have a secondary alkyl bromide, and we want to convert it to a primary alcohol. This is the primary alcohol we're trying to make. And this is it here. I'm just going to move this away from the arrow. Like that. Okay, how would we make that primary alcohol? Does anybody have an idea before I get into the nitty-gritty? Any kind of ideas? Yeah, somebody's saying use a hindered base again. So what Josh is saying is, what if you took this alkyl bromide and you treated it with a hindered base, like potassium T-butoxide? What's going to happen is you're going to make the Zaitsev alkene by an E2 mechanism. Okay? If we draw the negative charge on the oxygen, you could draw the E2 mechanism really quickly. Let me draw a proton in here. So you're going to get proton transfer, formation of the double bond, the alkene, loss of leaving group. Then how am I going to get from this terminal alkene to the primary alcohol? What would I do to affect this transformation? Yeah, absolutely, Josh. You're totally in the right vein. And I realize it's not easy to answer these questions over Teams sometimes, but in the first step, you're going to treat it with borane and THF. And in the second step, you're going to treat it with hydrogen peroxide, followed by sodium hydroxide. Why? Because this is just an anti-Markovnikov addition of H2O across that double bond. Hopefully you can tell by now that by the time you get to the end of Organic Chemistry 1, you pretty much have, reactions like this memorized, tattooed in your brain. You'll never forget them, right? Even if I see you on the street in 10 years and ask you, hey, you guys remember, anti-Markovnikov and Markovnikov addition? You say, yeah, I do. Let's try another one. 8.37D. We're going to take this tertiary alcohol. Yep, and we're going to make this compound. So we want to make this compound. We have this methyl group pointing up, and we have this hydroxyl pointing down. I'd say this one's a little more challenging than the other ones, but still a great question. Totally reasonable question for your quiz. How to go from this tertiary alcohol to this secondary alcohol? Look, I'm going to solve this one using retrosynthesis again. And if you're wondering, like, what do you mean by retrosynthesis? Look, for now, you can just call it thinking backwards. To make this question simpler, right? If I didn't want to ask you a question this difficult, I might say, how would you make that secondary alcohol from this alkene? What if I had this alkene? Could I go from here to here, really quickly and say, yeah, that's just an anti-Markovnikov addition of water, syn addition, right? The hydroxyl and the hydrogen both get added to the same face of the molecule. That's step one, is borane THF followed by hydrogen peroxide and sodium hydroxide. Hey, I know that one pretty well. Well, then the question then becomes, how do I go from this tertiary alcohol to this alkene? Now, does anybody have a strategy that they might want to employ to do that? And there's a couple of different ways to do it based off of what we've learned in class. Exactly. So Josh, you're totally in the right vein. Using toluene sulfonyl chloride to convert the hydroxyl into a good leaving group, absolutely. Yeah, because we got to do an elimination to make an alkene. Josh is saying toluene sulfonyl chloride and pyridine, which would give me the tosylate, which is a great leaving group, OTS. Then if I treat that, I've got my alpha carbon, I've got a beta carbon here, and I've got a beta carbon over here. If I was to treat that with a hindered base, sorry, did I label the two beta carbons the same? I didn't mean to do that. My mistake. I meant this beta carbon here. If I was to treat that with potassium T-butoxide, right, then I would remove a proton from the green beta carbon and I'd end up with this, but that doesn't help me. If I treat it with sodium ethoxide, which is a non-hindered base, I'm going to remove one of the beta protons and the beta carbon highlighted in blue, and I would end up with the alkene that I want. Right? I end up with the Zaitsev alkene. And then in the last steps, I'm just going to treat it with my borane and THF, followed by hydrogen peroxide and sodium hydroxide to do my syn addition of H2O, that is anti-Markovnikov. Anti-Mark. Okay. All right. .39. Let me go back to my blank sheet here. We'll try 8.39. 8.39a says, give me the reagents to go from this exocyclic alkene. So this is called methylene cyclohexene, methylene cyclohexane, to this 1-methyl cyclohexene. Anyhow, how would we do a transformation like that? And if you're, way ahead of me, if you're thinking, Mr. Dion, you're going too slow, you could try this one, where we have this alkene, and we want to make this alkene. Okay, for A, does anybody have an idea about what we could do for A? If you're unsure, thinking backwards from the product, what if I had this? What if I had a good leaving group at that carbon? If I had a good leaving group, then I could take a base like sodium ethoxide and I could just abstract that proton and make that compound, right? Using something like sodium ethoxide. So how would I put a good leaving group at this carbon? How do I put a good leaving group there? Yeah, somebody's saying add HBr, right? It would just be a Markovnikov addition of HBr. So HBr, this is Markovnikov addition. And I end up with a tertiary alkyl halide, the tertiary alkyl bromide. And then all I have to do is to treat it with sodium ethoxide. And I'm going to end up with the product. So that's just a 2-step synthesis. What about B? I'm going to let my students answer this one because we only have a few minutes left. Could anybody tell me where you might want to start with this one? So there's no hindered base required in B. I'm not sure if that's what my students put now or if that was written from before. But there's no hindered base required to go from this alkene to this tetrasubstituted alkene. If I had a good leaving group here, then all I would have to do is treat it with something like sodium ethoxide, which would remove the most hindered proton, which would give me this alkene. And so the question just becomes, how do I put a leaving group at this carbon that I'm highlighting in yellow? All I would have to do is treat that with HBr. That would be a Markovnikov addition. And I would have my bromine right here. Okay, and then all I have to do is treat it with an unhindered base like sodium ethoxide. Okie doke. Let's try one more, and then we'll call it a day. Let's try D. This is 8.39D. I'm going to start with this exocyclic alkene, and I want to make this alkene here. In terms of retrosynthesis, if I had a good leaving group over here, then I would treat it with an unhindered base, right? And it would remove this proton as opposed to, sorry, it would remove, no, sorry, then I want to use a hindered base. Sorry, I'm getting mixed up here. I would want to use a hindered base to remove the least hindered proton, because if I treated it with a non-hindered base, it would remove the proton in green, and I want to remove the blue one, right, to make the desired product. So how do I put a leaving group at this carbon that I have highlighted in yellow? Well, I'll just kind of do it quickly here because we're running out of time. But if you were to take this and treat it with HBr, you would end up with this tertiary alkyl halide, wouldn't you? Then if you were to take that and treat it with sodium ethoxide, right, you have either the green proton that you could abstract or the blue one, but you're going to pull off the blue one because it's going to give you the more stable alkene, and sodium ethoxide is a non-hindered base. So you'd have this. Now, how do I install a leaving group at this position? Well, in that case, I would use HBr and peroxides, which will affect an anti-Markovnikov addition of bromine. So now I've got our HBr across the double bond. And then if I treat this with a hindered base, like potassium T-butoxide, it's going to pull off this proton, right? If I draw the mechanism, it's going to abstract this proton, make the double bond, loss of leaving group like that. So how many total steps is that? It's 1, 2, 3, 4 steps.